I'm going to begin today by just talking a little bit about how to produce useful code. Because for those of you that came to the Python session a couple of weeks ago, you'll remember that we threw you in at the deep end and we went straight into using RDKit and doing some quite fancy stuff in Python. And today, I just want to take a bit of a step back. We'll have a little talk about what you should be doing whilst coding. And this is obviously all spoken about in terms of Python, but the ideas and the paradigms are exactly the same in whatever coding language you're going to use. And then I'm going to go on to showing you, and we'll do a bit of a code along with some examples of data types, of variables, of functions. And then later on, we're going to go into doing a bit of a small data analysis just to round everything off. But to begin with, what should we do to produce good, useful code? Well, the first thing we have to think about is the reasoning behind the code. And this is all about trying to understand the author's intent and trying to understand your own intent when you come back and look at the spaghetti soup that you made 6 months ago or a year ago. And when we look at it, we want to figure out what is it we wanted it to do, or what we want other people to be able to do with it. And if we can do that, it makes it much easier for us to modify it, for them to modify it. So when you need to identify something that needs changing, or you need to identify a use case, your life's a lot easier. And that's kind of in total conflict to what we do as scientists in a way, because in science, our job is to do science, and the software is just a tool to help us do that. And this leads to us using it as we would use a tool. We just put it in there, use it for what it's needed, and come out again. And this just does lead to, as we've said on screen, quick and dirty code. And it's difficult to understand then the reasoning behind. So if we start to look at this and frame this as from a developer's perspective, we'll start to be able to use it as a tool in a much, much better way. So this is a quote from the inventor of C++, and I'm not even going to try to pronounce his name. But basically, he says the most important aspect of software development is to be clear about what you're trying to build. So if you don't understand your code, you're not going to use it. If I don't understand your code, I'm not going to use it. And I can't hammer this home enough, the time you spend making your code easier to understand is going to be vastly, it's going to be very well spent time. And any time you spend here is going to be vastly outweighed by the time you save others and yourself in the future. And that's because, in a sense, your code is a living thing. You don't put it away and never look at it again. You go back to it, as I've said, a day, a week, a month, a year later. And if it's hard to reason now, you're not going to be able to reason what you've done then. So how do we help people reason about this code? Well, we could think about writing better code. We could think about writing good documentation, making use of a type system, and writing with appropriate style. And as you can see, I've kind of crossed out write better code, because I don't actually believe that writing better code, in inverted commas, leads to good readability. There are competitions where people try to solve a problem in as fewer lines of code as possible. And the complexity of the winners, the complexity of the code that the winners submit is incredible. So it might be very, very good, efficient code, but it's so complex that we have no idea what's happening. So I put in here on the right-hand side something called the Zen of Python. And you can find this by literally just typing import this into your Python notebooks or your Python terminal. And it's a bit of a philosophy, really. And it's seen in the world of Python as what you should be aiming for when you're writing code and programs. And so the lines that I've highlighted here, if you've not seen it before, is beautiful is better than ugly. So we need to make our code look good. Therefore, it'll be easy to read. Explicit is better than implicit. So be clear about what you're doing. Simple is better than complicated. As we've said, keep it simple. And if you have to go complicated, do it, but make sure it's simple and readable as possible. So a lot of the reason we use Python is because it's readable. And that's why we have all these indents and these curly brackets everywhere. And that's because your eye naturally follows that. And so the last two lines that I've highlighted here is if the implication is hard to explain, it's a bad idea. And if it's easy to explain, it's a good idea. And a lot of that, again, is just because of if you make the code readable, it's easier for you to explain. And if it's easy for you to explain, you're probably heading in the right direction. So I've put some examples in here of a Leonard Jones simulation that a friend of mine created, and he won't mind me picking apart some of his code because it's a good learning experience for him too. And what this does is it simulates the energy of some hydrogen atoms. And just looking at this, we're not really sure if it works properly just by looking at it. And we're not really too sure what's going on because there's a lot going on here. There's some things at the top for some functions. There's some constants, and then there's something at the bottom here that is calculating something, and then we're returning something down here. But what are these constants? I mean, this says n atoms, probably quite obvious. It's number of atoms, but T0 or sigma or box size or m, what do these relate to? What do these variables relate to? If you've just written it and you're familiar with this, you might know. But if you're coming into this or you haven't looked at this for so long, m's not going to mean anything to you. So when it comes to the calculation down here in this for loop, well, this looks pretty complicated. We're doing some group, we're timesing it by some number of atoms, we're finding, we're taking the mean away. But again, it's really, really not clear. And even I don't really know what's going on here. And as I say, I know the person that wrote it and I know why they wrote it. And if you write like this, it's great if you need to get something done quickly, but it's terrible if you need to come back to it at a later date. So if we look at another example, we've got some nested loops going on here. Why are they over different ranges? We don't know. This one's over a range of n atoms. This one's over a range of i+1 to n atoms. What are we getting out of that? There's some important functions here. There's no doc strings, so we don't actually know what this function is meant to do, and we're actually not sure what its output is meant to be. Because if we don't know what the output is meant to be, then how do we know that this function is working properly? And what are these checks for at the bottom too? And these are all questions that could very easily be answered by taking 5 minutes to write a little bit more about what's going on here. How do we do that? Well, one of the things we can do is write good documentation. And so we can use some inline comments where we put a hash and we write about what's going on. So we have a hashtag here and we say this updates location. Great. This hashtag here, right, this bit of code underneath, it gets the new accelerations. Great. We now know what it's doing. And if you write a hashtag and then something after it, you know that this bit of code isn't going to be executed when Python runs this script. And we can see here that this for loop that really doesn't mean anything if we just read it, it actually says if an atom has moved too far, pretend it has hit a wall. So now we know what these outputs are meant to be, and we know what the code's meant to be doing. Another way of documenting what we do is to write a doc string. And you put them in these 3 little quotes and 3 little quotes above and below. And here we can actually define what each of the parameters in our function is doing. We can define what is meant to be returned, and we can give a bit of information about how the function works. So if we come back to this, we have a really good idea of what's going on. One of the great things about using Jupyter and IPython is you can access doc strings. So if we use a function that is built in or that we've imported, we can press Shift Tab, and all of a sudden it will bring up here the doc string of that function. So we then know what's going on in there, and then we can use it properly. We can also write help and put whatever it is we want to use inside the brackets, and all of a sudden a load of information will come up about this. And that's great. This is, these are professional pieces of code that have been written, and this is something that we should try and emulate in our own code. So moving on from documentation and onto the typing, we start to get a little bit computer sciencey, but it's actually quite interesting because Python is what's called strongly dynamically typed. And so by strongly typed, it means that you can only do operations that are explicitly defined on that type. And that's really, really important. And with the type, you can't change it behind the scenes without you knowing about it. So essentially what I mean here is that if you have a type of variable in Python and then you change it, you will always know that it's been changed from one type to another. And this makes our code what's called type safe. And that's really important because you now get to a point where your code won't lead you down the garden path to a place where you don't want it to be. And it's the part that's dynamically, it means that you can change this variable type explicitly to what you want it to be, but it's you that is able to change it. So me as the author, rather than me as Python, if you say that something equals a string and it's now a number, it's fine with that. So with strongly typing, the language itself isn't going to change anything for you, but in dynamically typing, you can change things to whatever you want. And we can still use type hints here to make sure that our intent is clear. And we can use a type checker to check this. And this all comes together to make our code type safe. And so therefore we can, by doing type checking, we can get a bit more reasoning and understanding from our code. And we can see that if you write bad code with type hints, you can still understand what's going on. And if you write good code with type hints, you obviously can understand even more what's going on. So then we can move on to code style. And we want our code to look like other people's code. We want it to be pretty, as the Zen of Python said. And the style guide for Python is described in PEP 8. And so you can go and have a look at it and you can try and emulate how this all works. I wouldn't get too hung up on making your code conform to PEP 8 all the time, but definitely use it as a reference because as I've said at the bottom here, readability counts. And if you follow PEP 8 to a certain extent and you therefore make your code readable, yourself and other people can then reason what's going on in the code. So to summarize, as developers, we want to make our code and our programs as user-friendly as possible, and we need to make sure that our intent is clear. And you are the person that will be spending the most time reading your code. And so 5 minutes to do some commenting, to make some doc strings, and to write in a PEP 8 style now might save you hours in the future. And I've just end with some resources that some of you might like to look into if you want to look up some paradigms of programming a little bit further. I can highly recommend The Pragmatic Programmer and The Hitchhiker's Guide to Python. And they will really teach you how you should be writing code so that it is reproducible, easily accessible, and easily understandable. So